Okay, so our next example with complex numbers is getting total impedance. So it says, assume that we've got the inductor from the first example, impedance of an inductor, is connected in series with the capacitor from the second example, impedance of a capacitor, and a 100 ohm resistor. Find the total impedance, and a reminder that impedance is additive for series systems, and express the total in rectangular, polar, and exponential form. And so an inductor, if we remember, if you haven't really talked about these before, but the symbols for those is it looks kind of like a curly thing when we're drawing a circuit. A capacitor has kind of two bars, or sometimes you might see it as a bar and more of a curved second bar with the going. And a resistor is kind of a series of jags. So what we have going on, we have our previous inductor, which we calculated out to be 942 J ohms. So we've got these three things together. We've got an inductor, which Z is 9.42 J ohms. We've got a capacitor, in our example earlier, it had a Z value of negative 132.6 J ohms. And then, in addition to these, we've added a resistor, which has a Z of 100 ohms. And to add these up, the Z total is simply going to be, we'll call that one ZI, that one ZC, and that one ZR. It's ZI plus ZC plus ZR. So it is 9.42 J minus, or plus a negative, minus 132.6 J and plus 100. That's in the real plane. So Z total is 100 in the real direction. And if we add those two numbers together, 9.42 minus the 132.6, we get negative 123.2 in the J direction ohms. And so that would be our rectangular form. So there's part one. Then we would want to keep working with that and go for the polar form. And so remember, when we want to do polar form, that Z total is going to be some Z at theta, an angle. And the equations for that work the same way as if we had a 2D vector. That the magnitude of Z is going to be the square root of the real part, which is 100, plus the square root of the imaginary part, which is negative 123.2 squared. So let's put that in the calculator. Square root 100 squared plus negative 123.21 squared. Make sure we put that negative in parentheses. Otherwise, our calculator is going to give us bad information. So there you can see it's done the right way. And so we get that Z is 158.7 ohms, the magnitude of it. The direction of it, theta, we do by using the tan inverse of, remember it was the y part, this corresponds to the imaginary part here, so it's the negative 123.2 over the real part, which corresponded to the x. So theta is tan inverse of negative 123.2 divided by 100. There we go, tan inverse. So it's negative 50.9 degrees. And so we can say that in polar form, Z total is equal to 158.7 ohms at negative 50.9 degrees. And that generally has to do with what you would hear of as like a phase of the current. So that's polar form. And then the other way you see this referred to is exponential form, or using what they call Euler's formula to get there. So Euler, let's talk about that guy for a minute. It looks like Euler. Euler said that if Z is equal to the magnitude of Z times cosine theta plus Z times sine theta, that's, if it was in this form, that's the same as the magnitude of Z times cosine theta plus sine theta times the J term. And what he came up with is that this is the same as e to the j times theta. Now, we mentioned Kramer's rule last time. That one seems like something that, given enough time, one of us could come up with this. I have no idea how he got to this thing. If you're interested in that sort of thing, I suggest Google it, and I'm sure that you can find a derivation. So Euler says, well, if you have it in this form, if you know the angle, you can also write it like this. And so that's what we call our exponential form. We simply take our polar form and write it a different way. So then in exponential form, Z total is the 158.7 times e to the negative 50.9 degrees J. And that would still have units of ohms.